is find the corresponding transfer function. Okay, and the factors will be of this form. There will be a s over omega 1 raised to the n, and also plus or minus 1 plus or minus s over omega 1 raised to the n. So we want to find the appropriate factors. It could be a constant as well. So the transfer function, actually, see, when you remember when you're given magnitude, or I should say that the magnitude plot applies to any one of these different combinations here. Plus or minus can appear in either spot there. The magnitude is the same. So in that sense, there's more than one answer for the transfer function. And we also like to find this crossover point here. In fact, what you want to do first is look at the slope change at each break frequency. So in other words, break frequency is where the slope does change. Okay, so at this frequency here, and I can go ahead and put in the slope of these lines, right? This line here, notice that the slope at over 1 decade, it changes by 20 dB. Okay, right. So I'm talking about this line here. Over this 1 decade here to here, it goes from there up to that level, from this level to that level. Right, so that's a slope of 20 dB per decade. How about this line here? What is the slope of that line? 60. Yeah, see, over 1 decade, from here to here, what is how much does it change in terms of decibels? Right, from here to here, this line here goes from this level to that level, right? Minus 40 plus 20. That's 60 dB per decade. And so let me take out some of these hash lines here. This is 60 dB per decade. And this one here, over decades, it changes by 40 dB, or over 1 decade, it changes by 20 dB. So 20 dB per decade is where this one here is the slope. And this one is going to be minus 20. Per decade. And so, as I was saying, what I want to do, what would be helpful is to look at the slope change at each break frequency. So at this break frequency of 10, it goes from being 20 to 60. Okay, so the slope change is 40 dB per decade is possible. Okay, so right here we have delta slope is equal to 40. And you can write that as 2 times 20. Right? Okay. And how about this frequency here, 10 squared? It goes from being 60 to 20. So this is also 40 dB per decade here. I should say at this frequency here, right? At 100, the slope change, delta slope is equal to 40, or 2 times 20. Is that positive or negative? Negative. That's negative, right? And so minus 2 times 20. And then here, the last place where the slope changes, it goes from being plus 20 to minus 20. And therefore, the slope changes minus 40 dB per decade. And delta slope minus 40, which is minus 2 times 20. So now what we'd like is to start constructing the transfer function h of s. And the way to do that is to start with that factor that has an effect at low frequencies. So it's a factor corresponding to this line, to this straight line, right? It would go through 10Q. Okay. And another way of doing that, we could kind of draw the first couple here. Let's let this be 10Q. So, and this was 20 dB per decade. So what is the expression for this, right? This is 0 dB.
S over 10 to the third.
What is that?
S over 10 to the third.
Okay, so that's S over 10Q. Okay. And so now, remember that this is not the whole plot, right? What's happening is that at this point, we have a slope change of 2 times 20. Okay, and so the way that would work out would be this: you'd have 0 dB, and at that frequency of 10, it goes from being 0 to being positive. In fact, this is, what is this slope here?
40.
That's 40 dB per decade. And so this one is described by S over 10Q. This one is described by what?
1 minus S over 10 plus or minus 1 plus or minus S over 10 to the second. To the second power.
To the second power, right? In other words, this is this is equal to 2 times 20. Right? So it's this. Gives you the 2 there. Okay. And now, so this is what we have so far. I should put them like this, right? S over 10Q. Right? And all we have to do is take a look at the slope changes, right? Now we accounted for this one, the slope change of 2 times 20 there. And at this frequency, slope change of minus 2 times 20 corresponds to what?
Plus or minus 1 plus or minus S over 100 raised to the power of negative 2.
Yeah. In other words, it's a denominator factor. Okay. And then, what else do we have? We took care of this. A factor here. I should say we took care of that slope change, right? Which corresponded to that factor. And then the slope change here of minus 2 times 20 at 10 to the 4th is similar to this one, except that it's 10 to the 4th instead of 10 squared. So we've got plus or minus 1 plus or minus S over 10 to the 4th to the minus 2. So this is our H of S. Right, so we could rewrite that. You don't have to simplify it. You could leave it like this. Okay, so you've got S over 10 cubed, and let me put that 1 plus S over 10 squared, 1 plus S over 100 squared, 1 plus S over 10 to the 4th squared. So that's one possible transfer function. that describes this Bode diagram, straight line Bode diagram.
So, this is how you actually identify systems. You basically apply some impulse to the system and then look at the body plot and try to come up with a transfer function for it.
Yeah,
If you have like
you
a-
can experimentally identify the system by running a frequency response on it. In other words, apply a sinusoid and let the frequency of the sinusoid increase from low to high. And the output will be a sinusoid of the same frequency as the input. And the amplitude of the output will correspond to the magnitude versus frequency. Phase of the sinusoidal output will correspond to the phase plot of the Bode diagram of phase, or the frequency response of phase. So that's one way to experimentally determine it.
How about using impulse response? How about if you apply a kick to the system
You,
and then
Yeah.
look at the response?
you can apply an impulse to the system. And in other words, you've got a system, H of S, that is the transfer function that we're looking for. The physical system is described by this H of S that we'd like to find. But we can apply an impulse to the input. A unit impulse function has a Laplace transform of 1. Okay, and the output is therefore going to be H of S, or in the time domain, it's going to be H of T. So you have a time, you'll get a time response, right? With this applied, you get a something that looks like that, okay? And then
Convolution.
you could somehow you'd have to find the Laplace transfer function that corresponds to that. Okay, Laplace transform. Laplace transform of this gives you that. There's a section in the book also that talks about experimental determination of the transfer function. I'll talk about that. Let's see. So we found a possible transfer function, and so there's several possibilities here. Right? And the next thing we want to do is find omega 0. And these are omega 0. See, we want to take a look at this straight line here, and we want to write the equation of a straight line. We know its slope, okay, and so we can write y minus y0 equals m. Instead of x minus x0, it's going to be log base 10 of x minus log base 10 of x0. And so we know this point here, right? It is minus 40 at 10 radians per second. Okay, so this is our y and y0, y and x. Okay, and your y0 would be 0, right? In other words, we're looking for this. The y0 would be 0, and we're going to find the omega 0, which corresponds to the x0 here. So you've got y, which is minus 40, minus 0, y sub 0 is 0, is equal to the slope. The slope is 60. 60 times the log of x. X is at 10, right? Minus 40. So log 10 minus log of x0, or omega 0. So you've got minus 2/3 is equal to log 10 to the first, right? Is equal to 1. Is that 1 log of base 10? Base 10 to the first minus log of omega 0. Right, so log of omega 0 is equal to 1 plus 2/3 right, 5/3. So, under this omega 0 is going to be 10 to the 5/3. Right. Equal to 46.4, something like that. And so does that make sense now? In other words, this point here that we're saying is 46. Yeah, and it does make sense. Anybody tell me why?
Between 10 and 100.
Almost halfway.
It's between 10 and 100, right? But also, remember, okay, this is 10, and this is 100 squared. 2 and 5 roughly break up the decade into thirds. Right, so this is 2 and this is 5, and it falls close. Yeah.
So I get everything you're talking about, but I don't understand the delta slope. Could you
Oh,
explain that
oh,
one?
the delta slope, like this delta slope here.
Yes.
Well, this is 20 dB per decade. There's the slope of that line. The slope of this line here, what is it? Right, if we go through one decade, right, from 10 to 100, the slope changes from -40 to +20. Okay, and so, well, let me take it back. So this is 60 dB per decade. The slope of that line, the slope of this line is 20. What is the slope change?
Okay, so it'd be 40, because it's, oh, okay, I got you.
So that
It's literal
at that
change of
frequency, we have a slope change of 40. And I wrote it as 2 times 20 to help us
Put it in that form.
put it into the transfer function form there. This 2 here says, hey, it's a numerator factor raised to the second power.
I got you. Okay, thank you. That makes sense.
Other questions? Let me do another example. But on the homework, the first problem, it says you got the transfer function, right? And what does it ask for? It applies, you've got a sinusoid or a sum of sinusoids applied, and you want to find the output sinusoid, right? The output sinusoid. And that is all based on this, the fact that, you know, when you run a frequency response, right, you apply a sinusoid, like a sine or a cosine. Let's say it's a cosine of omega t. And you apply that to the system, and I don't know, I can't remember what the system transfer function was, something like 1 over or something. Anybody know?
10 over s plus 11.
S plus 11. So, all right, S plus 11. So, and so this is our H of S here, right? And so our H of J omega is going to be equal to the magnitude of H of J omega and at a certain phase of H of J omega. Right, or we could write that as the magnitude of H of J omega, either the J theta of omega, where theta of omega is identically the same as the phase of H of J omega. Right? And so the output here is going to be for an input which is has an amplitude of 1 and a frequency of omega, the output is going to be the magnitude of H of J omega, also a cosine of the same frequency, but there will be a phase shift of theta of omega. That's theta of omega there, right? And so all you really have to do is find the magnitude and phase of this at the particular frequency of the input sinusoid. like if the frequency of the input sinusoid is 2, no, let me make it 11. So the magnitude, right, of 1 over J11 plus 11, the magnitude of that I can factor out in 11, right? And it's 1 over 1 plus J1, right? And that's going to be 1 over 11, and the magnitude of that is going to be square root of 2 there, 1 plus J1. Okay, and so that would be the magnitude of the output sinusoid for a frequency of 11, right? And the phase, would be like minus 45 degrees, right? Because this has a phase of plus 45, bring it up in the numerator, so just change the sign. Okay, and actually what you have there is a sum of a sine and a cosine, right? And so, and it might be like, something like 2 cosine and 5 sine, right? It's just that the output is also going to be multiplied by those factors as well. And so if you have if you have 5 sine omega t plus 2, what you're going to get out is you get out the 2 here plus the magnitude, the 5 times the magnitude of h of j omega times the sine of omega t plus theta of omega. Is that reasonable? Did it look okay? All right. If you have a sum of the sine and cosine. Then the last problem, it was about a quadratic factor where the damping ratio is between 0 and 1, right? And wanted you to find the maximum magnitude error because the straight line approximations are so far. There's a lot of, depending on what the damping ratio is, there could be a lot of error. If you have something like 2 over s squared plus 2s plus 2, and you replace s by j omega, you got 2 over 2 minus omega squared plus j 2 omega, right? 2 square j omega, you get minus omega squared and 2j omega. And so for a given frequency, you can find the magnitude, right? The magnitude of this expression is 2 over the square root of the sum of the squares of the magnitudes, right? And so for a given frequency, you can evaluate the magnitude. In fact, you can evaluate the phase as well, right? And so you can find the phase, magnitude and phase, the exact magnitude and phase at a particular frequency. And from the straight line, you got the straight line Bode diagram, and you also got that from page 411, the exact plots, or you can do it by MATLAB, right? And you can use a cursor to find the at a certain frequency where the magnitude is maximum. You can find the error between the straight line and the maximum value. So, or you can do it by computation like that. So you just kind of eyeball where the maximum error occurs for magnitude or phase, and use that frequency to plug it in to evaluate. do some more Bodhi diagrams of magnitude and phase, if you would like that. So. Next week is the exam, right? It's Thursday, I think, a week from today. And so it would cover through Bodhi diagrams. Okay. Design using root locus design and the Bodhi diagrams.
For Bodhi diagrams, that's magnitude and phase.
Yeah, you want to be able to draw the straight line Bodhi diagrams of both magnitude and phase, or and you want to be able to identify a transfer function from a given magnitude plot, not from phase. So here's one, and maybe somebody can do it. H of S is equal to S over S plus 1 and minus 1 plus S. Okay. We want to draw the straight line Bodhi diagrams of magnitude and phase. Anybody like to come up and try that out? Okay. Oh, okay. The one there, as far as magnitude is concerned, doesn't matter, right?
Would you mind writing everything a little bigger off to the right?
Yeah, sure.
So I think he was asking about this. This
Yeah,
is-
I'll rewrite it in
Oh,
a
okay.
second. For this first one, S over 1 to the first power, it has a slope of 20 dB per decade, and it is 0 decibels at 1 radian per second. And the next one, also the negative 1 power, so it has a negative 20 dB per decade slope. And the last one also has a negative 20 dB per decade slope. And they both break at 1 radian per second.
And before that, there's
And before that is 0. Which means that from very small to 10 to the first, there's a negative 20 dB per decade slope. And then at 10 to the first, it'll slope downwards at negative 40.
It should be negative.
Negative 20 because of that. It's 20 minus 4.
and this would also continue down to the lowest
Yeah.
frequency. Thank you. So now there's phase as well, right? And the way to draw the phase, you could draw each individual, for each individual factor, draw the phase and then combine them. Let's see. So let me draw it like this right here. So this first factor, what is the phase of the first factor there? 90, it's constant, right? And so you have, say, 0 degrees and 90 there. So 90 degrees. So it's constant for all frequencies. And then you have this factor here. And let's see if I put 0. This is going to be a, in fact, I'll just use this as my reference line. And so it comes up to 1 decade below this frequency, right? And it's going to break there, and then it's going to break again at 1 decade above that frequency, 0.1 and 10. So here is 0.1 right here, right? So this is 0.1. So it's going to be 0 up until that point, and being this is -1, it's going to break downward at the rate of 45 degrees per decade, and it's going to end up there at for over 2 decades. It's -90 degrees at the end there, right? Minus 90 degrees, and then it flattens out. Okay. And how about the next one here? We have to look at that. Look carefully, right? You see, it's 1 over -1 plus s. right? We can replace S by J omega, because this is plot versus omega. And then take a look at low and high frequencies. At low frequencies, and not letting omega go to zero, basically, what you have is -1. What is the phase of -1? Plus or minus 180, right? And so let's use one of those. And what is it going to end up at? At very high frequencies, we can say eventually this term will be negligible, so we'll hide it. What is the phase there? -90, right? Bring the J up in the numerator. Okay, -90 degrees. So it goes from -180 to -90. It's increasing in phase, right? That's a nice way to look at the rate, change in phase, and in fact the lower and upper limits. So it goes from -180 to -90. Right? So let this be minus 180, and this be -90, and so over that same range from 0.1 to 10, it's going to start at low frequencies at 0, and then it's going to linearly increase, and then it's going to flatten out. Okay, so all we have to do is add these three up here. Right? This starts at this one contributes 90 at low frequencies, this one contributes 0, this one contributes -180. And therefore, at very low frequencies, it starts out at -90. Okay, so let me erase the magnitude now, and I'll put the composite up here. And then it starts out at -90, right? So this is 0 degrees, and this is -90 degrees. And so it starts out at -90 at low frequencies. And at 0.1, it is going to, what is it going to do?
Stay the same.
It's going to cancel out, right? Because this one is changing at the same, this was changing positively at the same rate that that's changing negatively. And, or you could say, let's look at this let's find the transfer function by looking at slope changes, right? There's a net slope change of 0 there at that frequency of 0.1, and so it stays flat. In fact, this is the phase plot there. So we did magnitude and phase. Maybe one other one here. Okay, so let's say we have h of s equals s plus 2 over s squared. Okay, we could write this as a couple of different ways. Right, this is we could factor that 2 out, right? So we have 2 over s squared, and we have 1 plus s over 2, right? And this s squared there, or that 2 over s squared, could be expressed as square root of 2 over s quantity squared. It could also be expressed as s over square root of 2 to the minus 1 times 1 plus s over 2.
The -2.
To the minus 2. Okay, and we could also express it as simply as an alternative going back here, you could express it as 2 times 1 over s squared times 1 plus s over 2, right? Or you could say 2 times s over 1 to the minus 2 and 1 plus s over 2. So you could choose either way. Okay, all right, let's choose the second way here and plot the magnitude. Okay, so let's see. I have a 2 here. Remember, 20 times the log of 2 is 6 dB. 20 times the log of square root of 2 is 3 dB, and so 20 times the log of 2 is 6 dB. So this factor right here contributes 6 dB. So if this is 0 dB, so we have right now, let's set, let me put this as 20 dB, then this is 10, and this is 5, and this is 6. All right, so it's a level here of 6 dB constant for all frequencies for that factor there. And then this factor here, it goes through 0 dB at 1 radian per second with a slope of minus 40 dB, minus 2 times 20. Okay, so that factor then, if this is our 0 dB line, right, and this is 1, right, 1, okay, 1. So it goes through there, and the slope is minus 40 dB per decade. And so, you know, eventually what we want to do is just add these up, right? And then the last factor there is a numerator factor, so it's going to break at 2. And so, you know, you could put it as a separate plot, 0 dB, and let this be 10. And so this 2 and 5 break up the decade into approximate thirds. And so it looks like this. And there's minus 20 dB per decade. So this is minus 20 dB per decade. And this is minus 40 there. And
Why is it minus?
oh, well, that's a good question. And plus 20. All right. Right. Or 1 times 20, right? And so power. Yeah, so all we have to do is add these up, right? And so we add these first 2 up. It basically shifts this up by 6 dB, right? 6 dB here. And so our composite down here starts at 0 dB. That it's going to be, in other words, it's going to look like this, except it's going to be shifted up by 6 dB at 1 radian per second, right? So at 1 radian per second, it's going to go through 6 dB, which is like here. And so it's going to go at the rate of 40 dB per decade. And then when it gets to 2, right there, 2, it's going to break. It's going to go from minus 40 to, you know, the slope change at that frequency of 2 is plus 20, right? Plus 20 from minus 40 to
From minus 40 to minus 20.
from minus 40, the slope here changes by 20, right? So this is going to be minus 20. So this is minus 40, and so minus 20 might look like that. So this is a complete Bode diagram of magnitude, right? From the lowest frequency, highest frequency, going like that. And so this right here is say some x0, right? That we might like to find, right? You can find it the same way that we did before. Right? We have the values of 6 dB at 1 radian per second, right? And we have 0 dB at the x sub 0, right? So it's a, y minus y0 equals m times x minus x0, where the slope, see on that interval where we want to find x0, that interval has a slope, the slope is minus 40. And so we have 6 minus 0 is equal to minus 40 times, that's 6, that's 6, that's at 1 radian per second, right? So this is 1 radian per second, 6. So log of 1, right, which is 0, minus log of x0. So I have one unknown in there. And this is 0. Right? And so this is equal to 6 over minus 40 is equal to log of x0, or right, 3 over 20. Right, so x0 is equal to 10 to the 3 over 20. And 3 over 20 is 1.41, is equal to square root of 2. So this x0 here is the square root of 2. So find that way. And then what we want to do is plot the phase, right? The phase of each of these factors. What is the phase of 2? 0, right? It's positive real on the positive real axis, phase is measured relative to the positive real axis, therefore 0. What is the phase of this factor here?
So 1 over j over this negative 1.
Yeah.
So it would be negative 180.
Yeah, plus or minus 180, right? So again, you have j omega over 1, right, to the minus 2, or, you would say 1 over j omega to the square, right, and this itself has a phase of minus 90, but it's square, therefore minus 180, right? So this has a phase of 0, this has a phase of minus 180, and this, so we have 0 degrees and minus 180, and then the other factor there, 1 plus s over 2. Remember, it breaks 1 decade below that, and then 1 decade above that. And it's a numerator factor, so it's going to break upward. And at a slope, since it's raised to the first power, the slope is 45 degrees per decade. And so it would look like this. At 0.2, it would break upward, and then at 20, it'll settle out. And so this over two decades, in other words, 0.2 to 20, 45 degrees per decade, this is going to go up to 90 degrees. So you start out at low frequencies for the composite. You see there's a 0 contribution from this, and so if this is 0 degrees, it starts out at minus 180 degrees, and at 0.2, it's going to start breaking upward, and it's going to change from 0 to 90 degrees. So this will go from minus 180 to minus 90 degrees. And so it starts here at low frequencies, and then it starts linearly increasing up to there, and then it flattens out at minus 90. Okay. And we also can check this, right? We can look at the original transfer function there, replace s by j omega, and let omega be very small and very large, right? So let's say 2 plus j omega over minus omega squared, right? When you square j omega, you get minus omega squared. And for, this omega squared is always positive, right? Because omega itself is always positive. Therefore, this is always negative here, and contributing a phase of 180. And so you say, all right, hey, what about if omega is really small? You've got a negative 2. Basically, negative 2 over omega squared, right? Minus 2 over omega squared. But this is always positive, and so it's always going to be 180, right? And that's what it started out with. At low frequency, it's at plus or minus 180, okay? Of course, you could add 360 to this, you get 180, and add 360 to that, you get 270. So you could look at it like that as well. And then at very high frequencies now, at very high frequencies, at very low frequencies, what we said, we throw that away, right? Compared to that. So the way we get that 2 over minus omega squared. At very high frequencies, we do just the opposite. We're going to throw this away, right? And so what you have is minus j 1 over omega, right? If I did the math correctly, minus j 1 over omega. And this right here is always positive, and therefore this minus j is along the negative imaginary axis, right? And so it's pointing down like that, and therefore that phase is minus 90. So that's where it ends up at the high frequencies at the phase of minus 90. Yeah.
I have a question about the S over 1 term. In this example, for the magnitude, the S over 1 intercepted the x-axis at 1. But in the previous example, the S over 1 term intercepted at 0.1. And I was wondering what caused it to intercept 0.1.
The previous example, are you talking about
That one, correct?
this one here?
Yeah, so for that S over 1, it's raised to the first power.
This S over 1 here. Right. This term here will always look like this. In fact, you see it, and why? 0 dB, it'll go through 0 dB at 1 radian per second, and it will have a slope of 1 times 20, or 20 dB per decade. 20 dB per decade. That's what it is.
Okay, so
And why? Okay, you replace S by j omega, you got j omega over 1, right? And we want the magnitude of that, which is just omega, and we want 20 times the log of the magnitude of that base 10 versus log base 10, right? And so it's going to be a straight line. And at the frequency of 1, you can see that at a frequency of 1, it's going to be, let's see,
Magnitude 1 to 0 dB.
yeah, it's going to be 0, right? 20 times the log of 1 is 0. Okay, and so you get 0 at omega equal to 0.1, it's going to be 0.1 is going to be minus 20, right? Minus 20, you get that, right? And so you get that line. Okay.
question. Kind of maybe similar on that question. On that one right there, on that graph, you started at 0.1 on this one, you started at 0.2 on that one. Where's the 0.1 in this one?
Why did I start at 0.1 on this?
Correct. And
Okay,
did you start
why?
with
Because the break frequency for either one of these cases is 0.1, 1 decade below that, and then it breaks again at 1 decade above that. So at 0.1 and at 10, right? This is 0.1. This is 10, right? So, and over here, let's see, which one are you talking about now? This factor here?
Well, on that graph right there,
Wait a minute, this graph?
yeah, it said now we started at 0.2 now.
This one started at 0.2 and it ended up at 20. In other words, 1 decade below this and 1 decade above that. Okay, just like this one, 1 decade below this and one decade above that.
I'm a little confused as to how the 6 dB over there kind of shifted the graph over to like a root 2. Can you explain that?
Yeah, right. In other words, this is 6 dB here. See, this one here goes through 0 dB at 1 radian per second. So if you add these two up, right, it's just going to shift it up. And so it is shifted up here, right? It was going through this here, right? Like this. It was coming down and going through 1, but then it shifted up. So at 1 radian per second, instead of going through 0 dB like this one, it's going to go through 6 dB here.
So does that mean that like if you continued that minus 40 dB per decade line to the left, that it would cross through 46 dB?
Yeah.
Okay.
Yeah, exactly. This is, in other words, if you go one decade below this, right, which is going to be 0.1, it's going to be, at this point, it's going to be 46. Yeah.
So likewise, if you're looking at the third one where it starts at 0 and then it increases at 20,
Let me see which one.
right there.
This one
Yes,
starts at
0 and goes up by 20, right there.
this one. Yes. Okay.
So we're kind of like combining, I know, on all three of them together, you know, the 6 dB, so we're shifting up the first one by 6, and the second one should also be shifted up by 6, correct?
Well, this one here, this one here is 0 all the way up. It doesn't come in, it doesn't kick in until 2, right? So that's where it kicks in there, and the slope goes from minus 40 to minus 20. Okay. Yeah.
My question is where the 6 dB came from.
The which dB?
The 6 dB, like where did it come from?
The 6 dB. That 6 dB came from
The two
from this here, 20 times the log of 2. Is 6 dB. Actually 6 point something, 01 or 02. We have other questions.
Do we have to memorize the dB values of 2 and like constants like 2, 35, stuff like that?
You don't have to memorize it. I'll make it such that the numbers work out.
Okay.
Okay.
So like, you would give us 10, right? You would give us a constant like 10.
Yeah.
100 or something.
Yeah, or 100, right. Other questions? Okay, now let's move on a little bit, and this is we've been graphing complex functions here, but what we want to do is introduce a new graph. Okay, I'm going to start from basics. does that mean?
Function of the
Function
The
of x.
value of the function evaluated at x.
Yeah, so it means given a real value x on the real line, you find a real value on the real line f of x, right? So you can look at that as a mapping. You're mapping from the real line to another real line, okay? And, right, so in other words, you're mapping from the x to the f of x, right? So, for example, if you have f of x is equal to x squared, right? So if x is 0, you get 0. If x is 2, you get 4. If x is minus 2, you also get 4. Now, let's consider mapping from the complex S plane to a complex f of x plane. So, right, this is mapping from a plane to another plane. Okay, so you have some f of s, right? And you've got S there is complex. It's a sigma plus j omega, right? And so it can be depicted for any value of S can be depicted in the S plane. And this is imaginary, and that's real. And for any given value of S in this S plane, we get a complex value of f of S, right? It's in general complex because S is complex. And so we have this f of S plane, the f of S plane, imaginary, of f of S, and the real of f of S. Okay, and for example, and by the way, this is the independent variable. This is the dependent variable there, right? And likewise, the S is the independent complex variable, and the f of S is the complex dependent variable. Okay, and so for example, if you have if f of f is simply 1 over s, and if s is equal to minus 1 plus j1, right, then you can find f of s, right? And f of s is going to be equal to 1 over minus 1 plus j, minus 1 plus j1, right, which you can express as 1 over this is a square root of 2 at an angle of 135, right? In e to the j 135. And so this can be expressed as 1 over square root of 2 e to the minus j 135. So the 1 plus j1 here, 1, j1, this point right here maps into 1 over square root of 2 at angle minus 135. So minus 135 will be down here, and it would be the size is 0.707, right? And so this is 0.7, so let's say that this is the point, okay? And so this has a face of minus 135, and it has a length, a vector length of 0.707. 0.707, yeah. And so now, you can plot regarding control systems, right? Oh, and the other thing I wanted to say was that x naturally takes on values. Normally, when you plot f of x, you let x take on successively larger and larger values, right? But in the S-plane, there is no natural succession of points from one point to the next, as there is in the X line there. And so it really depends, it really depends on the particular application. Depends on the particular application. So for example, let's consider the frequency response. The frequency response of a system. In fact, let me draw that little diagram, the little block diagram. So we have your control system here, and this is G of S, right? And let's say it's unity feedback. Okay. When you consider the frequency response, and you have you're given some G of S, what you do is replace S by J omega. So in this case, you're going up the J omega axis, right? When you're interested in the frequency response. So in the along this in this S plane, you go up the J omega axis from a 0 all the way up towards infinity, right? And that's one application when you're dealing with a frequency response. If the question is control system stability, then there is a specific S-plane contour. Okay, so this is for the frequency response. Set S equal J omega. Regarding stability, our S-plane contour goes up the J omega axis all the way to J infinity. It goes around that infinite radius semicircle, and it's infinite radius, therefore, this would be at infinity, right? And it has this particular direction, right? Comes around like that, and then comes back up the J omega axis. So here, when we're considering control system stability, our S-plane contour of relevant S-plane contour is that one that encloses the whole right half plane. Okay, and it has this closed clockwise direction, right? And this is it goes up to infinity, right? And this is down there minus J infinity. And the right half plane, as you can kind of imagine, is the right place to be, because that's for unstable systems. Okay.
So what would be the mapping of the right half plane to F of S plane?
Well,
if it's a stable system.
If it's a stable system, the mapping would be such that I can't completely answer it because we need a little bit more background, but the mapping would be, in many cases, such that the point -1 is not enclosed by that mapping of G of S.
So do you map G
With
of
this
S?
map. Sorry?
Do you map G of S or the closed loop transfer function?
G of S. To determine stability, we're going to map G of S. We're going to map points along this and this specific contour into the plane of G of S. And you'll see as we move along why that is. Okay. So, next time, give some examples and consider what's called the Cauchy principle. Yeah.
It's gonna be in the next. Which was it?